The Van probes right now are in a stable orbit, and if they remained there, they could be in orbit for hundreds or thousands of years.
Because there's nothing to slow them down, there's nothing to remove energy from their orbits.
All of the missions now need to deorbit their spacecraft at the end of their lifetime so that we don't end up with space junk. We're performing a series of maneuvers on the Van probe spacecraft in order to change the orbits.
Next year, we won't have enough fuel to do this kind of a maneuver. This is our only chance to get our spacecraft to the orbit that we want.
The Van Allen probes have really provided us with more than 6 years of non-stop excitement, continually bringing us wonderful science results, incredible observations from the heart of the most intense radiation region that really humanity has ever found.
The radiation belts exist across the solar system and probably across the entire universe at all bodies that have their own magnetic field like we have at Earth.
But they are very, very susceptible to changes in the solar wind.
During geomagnetic storms, they can completely disappear and then come back with much, much higher intensity.
So spacecraft that aren't normally in them can suddenly become engulfed by them. And so it's really critical for us that we understand how these radiation belts are changing so we can better design spacecraft to be able to withstand unexpected dosage of radiation.
So understanding the fundamental science is absolutely required in order to make predictive model relevant to space weather.
Having the two satellites, you get two simultaneous measurements of different parts in the belts, and that gives more of a global picture of what's going on with solar weather and with the radiation belts over time.
Their orbits are a little bit shifted, so instead of having them overlay on top of each other, they're moved a bit to the side.
We try to plan and create opportunities for them to pass near to each other, which presents an opportunity for the scientists to have short-range correlation of the data and also to take measurements along the same magnetic field line.
We have this highly elliptic orbit in order for the spacecraft to go through all of the different areas of the Van Allen radiation belts. So it really gets a great picture for the scientists of what's going on in the different regions.
The Van Allen radiation belt probes have really shown us just how dynamic and how exciting this region of space is.
And prior to our mission, were considered as a relatively boring and uninteresting and well understood field. Our mission turned it completely around and made it into a complete new science exploration, vibrant field by making a number of unexpected scientific discoveries.
We actually launched them. We really thought they were just two belts. Very soon after we'd launched, we discovered that the outer belt can actually split and form two belts itself, giving us a three-belt structure. But we were able to really watch how that third belt formed, how it changed, and then eventually how it diminished and just sort of got sucked back into the original radiation belt.
Over the course of the mission, we've taken over 8,500 contacts, and that's about 18,000 hours of contact time. Because the dish and the Mission Operations Center are co-located at EPL, we have a lot more time available on our antenna.
We not only downloaded every day 3 times more than the science data that we were required to our scientists. We published about 560 papers across the globe.
Right now, every 3 days, someone in the world is publishing a paper based on the Van Allen probes data.
The Van Allen probes are powered from our solar panels, and so we need to make sure that the solar panels are always pointed towards the sun. The spacecraft will naturally precess, it'll move off of the sun, and we use the propellant in order to push the spacecraft back to make sure that it maintains that attitude. Once we run out of propellant, we don't have that ability to control the spacecraft attitude anymore.
We are using actually a large amount of fuel to change this orbit from 370 miles to 190 miles.
Each burn is 2 hours long, and we'll be using a little under 4.5 pounds of propellant.
And since we have fuel now, we need to deorbit, change the perigee closer to Earth to make sure in the next 25 years we are down.
These are by far the largest maneuvers we've done to date.
We're going to be executing 5 burns over the course of 2 weeks when the orbits are in the proper orientation to really have the most efficient burns possible and save the most propellant to be able to do science as long as we can.
The fact that the spacecraft and those instruments have survived more than 6 years in really what is the most intense radiation region that we know is just incredible.
This mission was about resiliency in the harshest environment that no other spacecraft was able to take. This mission was making the impossible possible. And we really did it by a great, talented team that we had, the hard work that they put, and the collaboration across different disciplines to make this happen. And we really couldn't be more proud of what we've accomplished.